How does he make sure to whack everybody in the back?
All right, we're all very excited to have Austin here in person and to hear about stretching a black hole. So whenever you're ready.
Okay, thanks. Yeah, so it's great to be here in person. I haven't given an in-person talk in like 2 years, so it's kind of fun. For those of you who don't know me, my name's Austin Joyce. I just started in the Astro department over there, so hopefully you will see more of me in the future. Thanks for the invitation to give this talk. And so today I'm going to tell you about some recent work I did with Lam Hui, Ricardo Penco, Lucas Antoni, and Adam Solomon. And I'll explain what this kind of silly sounding title is about. And really what it's going to be about is about deformabilities or static responses of black holes in general relativity. Just to kill all the suspense, the answer is no. So if all you cared about was the answer, thank you for coming. It was great to see everybody. But okay, so first I have to explain what this question even means. Right? So what am I even talking about? And then it's usually a good thing in physics to explain why we care about things. So you might say, why is this even an interesting question to ask? Okay. And then, since I told you the answer is no, you might reasonably ask why can't you? I'll explain also why that's the case. Okay. I should also, can everyone see everything? And please feel free to interrupt me. I purposely gave a Blackboard talk so that it can be kind of informal. Okay, so let's start in the middle. Sorry. Okay, so the first, let's start in the middle. Why is this an interesting question? Why am I asking this question? And roughly speaking, it's because we know that black holes are like these deeply mysterious objects fundamentally. They have deep mysteries associated with them, like the information paradox, things like this. But at the same time, if you're an observer outside of black holes, they seem like extremely simple. Right? So we know that sort of no-hair theorems imply that black holes sort of depend only on things like mass, charge, and spin, or let's say characterized by mass, charge, and spin. And so they're really amongst the simplest possible objects that you can imagine. So there's actually a nice quote by Chandrasekhar about this, where he says, something like black holes are the most perfect macroscopic objects in the universe because the only elements in their construction are our concepts of space and time. They're like things built out of gravity, characterized by very simple parameters. Okay, but nevertheless, so despite being such simple objects, if you try to think of them as non-mysterious, if I'm an external observer, there are various things I might want to do to a black hole. I might want to, I don't know, hit it with a hammer, throw something into it, put it in an electromagnetic background, and sort of see how it responds to things. Right, so the philosophy is sort of going to be like, let's treat black holes like ordinary objects. See what happens. So this is sort of a theoretical question that you might reasonably want to ask. Like in principle, I can compute how they respond to an impulse or something just by knowing their mass, charge, and spin and GR, but I might want to have some other characterization of these responses. And it's also a experimentally or observationally useful thing to think about because these types of responses are sort of what we measure about black holes. So a type of response are, for example, quasi-normal modes. Well, these are the things that we actually measure in the ring down signals and gravitational waves. You might want to compute these quasi-normal modes. You might want to ask something about the deformabilities of black holes in a binary. That's the thing we're going to be mostly interested about, things like susceptibilities or static responses. And these things are, not just of academic interest because they actually do enter at some post-Newtonian order in gravitational waveforms. So these things are, in principle, measurable quantities. And so it's interesting and useful to learn about their properties. Okay. All right. So the type of response that I want to focus on is the following thing. So if I place an object in like a long wavelength tidal gravitational field, what happens is that it will mechanically deform or stretch in response. So tidal gravitational fields, let's say tidal, I'll just write like Riemann tensor induces stretching. So mechanical deformation of the object. And then the response of an object to this tidal gravitational field is characterized by these so-called love numbers. They're so-called because they're named after some guy, Love, who first computed these things for the Earth. So he wanted to measure or characterize how the Earth deformed because of the presence of the moon. Okay, so what do we want to do? So our goal is to calculate these things for a black hole and understand properties. So I should say the emphasis is really going to be on this like understand part of the goal, because these things were calculated in general relativity many years ago. I think they were first calculated in, I don't know, depending upon how you count, either 2005 or 2009. So these things have long been computed, but they're slightly mysterious for reasons that I will make clear. Okay, so here is the outline. Okay, so first I have to introduce a little bit of formalism. So I'm going to talk a little bit about point particle EFT. Sort of the formalism in which we're going to ask and answer these questions. Then I have to talk a little bit about black hole perturbation theory. And in particular, I'm going to be interested in symmetries that arise in the setup. Okay, and then there'll be some like summary kind of stuff. Are there any questions at this motivational level? Great. Everyone's totally happy. Fantastic.
The love number is the Newtonian concept.
Yeah, so in general relativity, let's talk in 4 dimensions. So in 4-dimensional GR, there's like an electric and a magnetic love number. The electric love number survives the non-relativistic limit, and so can exist in the Newtonian theory. The magnetic one is kind of more relativistic. But this, yeah, I mean, roughly speaking, what Love was characterizing were essentially Newtonian love numbers. Okay, good. Okay, so here's just a very quick reminder about point particle EFT. So this is, we want to think about black holes as point particles. So first, point particle EFT is a very long and old subject. I think the application to black hole physics was at least most nicely pointed out by Goldberger and Rothstein in about 2004. And that's sort of the type of formalism that I'm going to follow. But the idea, roughly speaking, is you have any object you like, it has some characteristic size that I'll call R. If you go extremely far away from this object, so at distances much, much bigger than R, all objects just look like point particles if you go far enough away. So the idea is that we're going to endow this point particle with some world line and write down some effective field theory that couples to this world line of a point particle. Okay. And at lowest order, the effective description is really just that of a point particle. So the world line EFT we write down is really just the induced metric. And then there are higher derivative corrections that we can write down, and the higher derivative corrections that we write down capture the composition of this object. And so philosophically, this is just like the multipole expansion of electrostatics. You know, there's like some monopole, and then if you can measure the electric field to finer and finer precision, you can start to learn something about the distribution of charges. You can measure the dipole and the quadrupole, things like that. Okay. So what is the simplest example where we can think about this? This example will sort of be like a toy model for a black hole. So let's think about a charged particle. Yes.
Are these eternal black holes?
I'm going to, let's see. So I'm going to think of everything sort of in the classical regime. So I guess I will assume they're eternal, but you could also imagine that this description is valid on length scales much shorter than the lifetime of the black hole.
So like on a Penrose diagram, this world line would basically be like along the horizon.
Good. So what I'm not really sure how I would draw a Penrose diagram for this. I just want to think of it as like a point particle. So I want to integrate over the internal degrees of freedom of the black hole. So I'm kind of throwing away some information about the global structure, and I just want to imagine that, you know, if I have a black hole and I have a table, if I go far enough away, I can't tell the difference between the two of them. And so I want to write some effective description. And the way I'll figure out it's a black hole is that there are some higher derivative couplings here, and the precise numbers that appear there will be special for a black hole, or then there'll be other numbers for an object like a table or something. I'll show you more in detail in a minute. Yes.
So for, I guess in this limit, you're assuming that the singularity is ignorable, right? The topology of your space is not missing some, like you don't have some missing points in your space inside your point particle.
Yeah. I mean, so it's an important point actually. There's sort of no inside to the point particle. The point particle is literally a point, and the way I figure out that it has additional structure is through these like non-minimal couplings between its world line to fields that I can probe the black hole with. So I'll show you an extremely explicit example. So let's just imagine that I have a point particle and I want to couple it to electromagnetism. And now even in principle, this point particle could be a black hole. So that the only thing it will change are the precise Wilson coefficients appearing in this EFT. So if I want to couple to electromagnetism, there's like a bulk Maxwell term. Then I want to write down some couplings on the world line of this point particle. Okay, and I'm going to switch to like a Polyakov kind of formulation. This is like the Nebugoto way of writing things. So I'm going to introduce a world line Einbein, I guess. Okay, so this is all just the free propagation part, and now here I want to put in some couplings between the bulk photon and the world line of the particles. This is sort of the minimal derivative coupling I can write down, and this really just is the charge of the particle. It's like a direct coupling to the photon. And then I can imagine writing down higher derivative couplings. And at leading order and derivatives, there are just two things you can write down. Okay, yeah, so I should say the point particle has like some pore velocity, so I'm allowed to use that as an ingredient in my EFT. So there's a coupling of the following form. And then there's a coupling which is just and then there are possibly higher derivative couplings with more F's and more derivatives and stuff like that. Okay. And so the identity of this point particle is then encoded in the precise numbers C1 and C2. These things characterized through like the Wilson coefficients of this effective sphere. Okay. And here I've chosen to sort of put in some scale, and I always have in mind that the scale is roughly speaking the size of the object. That's sort of your natural expectation. But you can see because of this scale appearing here that these are really capturing finite size effects, capturing the internal structure of this object. Okay.
So
And-
they are all
Yeah, sorry.
quadratic in A. So
Yeah, that's just for simplicity. I've just written the lowest. You can write f cubed. Well, f cubed actually.
no, but is there other linear in A terms?
Other linear in A terms.
Quadruple moments, etc. They are all quadratic.
Oh yeah, I think yes, yeah. So this is like a monopole charge. You could write down things which have like derivatives of A coupling to more dx views, and those would be like higher multipole charges that the object like intrinsically carries. Right. Yes.
You also include extrinsic curvature, like at this length scale of like what? I would have thought you also have like the extrinsic curvature as well.
Oh yeah. Yeah, but the things I'm going to be interested in are the couplings, like the minimal derivative couplings between the particle to external sources. So indeed, there are also like self-couplings, which are things like extrinsic curvatures and stuff like that. But I mean, the setup, what I'm going to want to do is to have this point particle like sitting there, and I'm going to like probe it with an electric field or a tidal field or something like that. So the things I care about are the couplings of those external fields to the point particle. Okay, good. Okay, so these okay, yeah, there's this like sort of cute canonical way of seeing, like if you think of the world line now as like the world line of an air molecule or something like that, these are the minimal derivative couplings to photons or to electromagnetism. And so if you wanted to do something like compute the scattering cross-section of photons off of air molecules in the atmosphere, you would see the cross-section goes like energy to the fourth, because each of these things goes like energy squared. And that's like exactly the way that Rayleigh scattering scales. And so you can see like the sky is blue from dimensional analysis by doing this kind of point particle EFT. So it's kind of like some cute application of this type of philosophy. But the thing that I'm going to be interested in are static responses. So these couplings control like the scattering, like two photons in. Sorry, I'll start with this one. Like a photon and this point particle come in, a photon and this point particle come out. This type of process is governed by these types of interactions, but these types of interactions also govern the response. When I turn on some background electric field, for example, then the object will polarize in response, for example, and then there will be some subleading electric field that I want to read off. So that's sort of the idea of what a static response is, and that's also governed by these same couplings, right? So very roughly speaking, a prototype for static response is precisely electric polarizability. In the context of this charged particle example, let's think about electric polarizability. Okay, how does this work? The idea, roughly speaking, is I have an object. So it's all kind of familiar stuff from undergrad E&M. I put it in some background electric field. And what happens is that in the presence of some background electric field, the charges in the object rearrange themselves and generate some induced electric field, which has a different radial dependence. So if we want to compute dipole polarizability, what we do is we apply a constant electric field. E equals constant. And what will happen is that the charges in the object will deform, and there will now be some subleading fall off where for dipole polarizability, there's some induced electric field that goes like the polarizability of the object over r cubed in this case. And so if you have a really good electric field detector at infinity, you turn on an electric field and then you extract the 1 over r cubed induced electric field profile, and you call the ratio of these two fall-offs the electric polarizability of the object. Okay, is that clear? Because the thing where you're going to want to compute in the black hole context is like exactly the same thing, just for gravity. So they're just more indices, but philosophically it's exactly the same. So is that clear? But let me show you how you calculate this thing. Okay. So let's compute this in the EFT. So I can, so these things are not literally E and B, but one linear combination is E and the other one is B. So let's imagine that I rewrite this thing so that this second line is C1 over R cubed squared plus C2 E squared. And little hats because they're not literally C1 and C2, but roughly speaking, they're the same. So what am I going to do? I'm going to turn on some sources such that the background field profile for E, let's say, is some E naught equals constant. So I'm going to turn on some sources such that there's some background E, which is some constant that I guess I call C. Okay. And then what we're going to do is perturbatively solve the equation of motion with this as sort of the background field value. And you can see what's going to happen is that if I perturb E around this background C at linear order in the fields, this thing will behave like a source. Okay. And so now the Maxwell equations that I want to solve are something like the following. Okay, there's some effective source, which in detail is like UC1 cubed. It's a static particle, so it just has a delta function. Okay, there's some world line integral. It's not particularly important, but just to be totally explicit. There's some source localized at the position of the point particle. Okay. Okay, so then using standard techniques like Green's function, blah, 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 you can just solve these equations. And what you find is that the induced electric field looks like the following. Details are not super important. R direction. So this is the induced electric field. Notice as advertised, it goes like 1 over R cubed. And so we can combine these things together. So the full solution is the following. E is ER, or sorry, E in the radial direction, ER0, which is just the amplitude of the imposed field, 1 minus 2 C1 R cubed. Okay. And the ratio of this term to that term, or said the other way, the ratio of this term to that term is the thing that we usually call the polarizability. So the polarizability here is minus 2 C1 R cubed. Okay. You can look this up in a book or something, but that is how the polarizability scales for the size of a standard object. But notice it depends on this free coefficient C1.
What happened to the position of the particle here? Why is it staying in place?
Oh, that was my choice. I'm going to just imagine that it's sitting still.
The equation of motion of the particle in the field.
I'm not, no, I'm just going to imagine that it's sitting still. Yeah, so if it had, so another way of saying it is I'm going to assume, I guess, that it doesn't have a bare charge so that the electric field doesn't make it move. So I'm just like computing some induced dipolar charge by putting it in an electric field. So you think of it as like a neutral object. Okay, so I'm going to do a microscopic calculation where the point particle is a charged sphere, where that's like a consistent thing to do. But okay, if you had a charged object, that would not be a totally consistent thing to do. Yes, that's right. Okay. All right, so this thing, everything I've told you is completely correct, but this polarizability is like totally useless because it depends on this C1, which I don't know. So if you ask me to like tell you how this object responds to things, I have no idea. So what we need to do is we need to calculate the C1. So how do we calculate the C1? What we do is we match to some UV calculation. And here UV just means classical Maxwell electromagnetism. All right, so what I'm going to do is imagine that the particle is a charged sphere. Sorry, not a charged sphere, a conducting sphere. So I won't really belabor the point. You all know how to do this. Roughly speaking, what we want to do is we want to solve like the Poisson equation for the potential, the electrostatic potential, but we have to decide what the boundary conditions are. So in this way of doing like point particle EFT, what always happens is that these Wilson coefficients in the UV theory, they're really they're encoding something about or they're determined by the boundary conditions that I choose to solve the UV equations of motion with respect to. Okay, so the boundary conditions, the first one is really just that I'm imposing a tidal field. So I'm going to impose that the E field in infinity, E at infinity is a constant. So that corresponds to demanding that the potential in infinity is like E naught in the R direction, R and theta. For R much bigger than the size of the object. And then the second thing, here's where I'm going to put in the information that this is a conducting sphere. I'm going to demand that the potential goes to 0 at the surface of the object, which I'm going to take to be capital R. Okay. Then you can solve the Poisson equation. It's easy. What you find is that E of R is a function of R. E0 of R. Okay, great. So now I compare my EFT calculation with my UV theory calculation. And what I infer is that C1 is -1. Okay, that's great. This doesn't do me very much good for this particular calculation, but now once I've fixed C1 once and for all, now I can compute any process I want that involves this operator. I now have a completely predictive EFT, which will tell me how a conducting sphere would respond in that case. So you can compute scattering of photons off of a conducting sphere, things like that, using this EFT. Okay, so this is like a very toy model, but you can now reasonably ask, I mean, even in the same EFT, we don't have to change the EFT. You can ask what happens if actually this particle is not a conducting sphere, but instead it's a black hole. What really changes about the story? Okay, so I could just ask that question already in this EFT of like a charged particle, and I could compute how a black hole responds, like the dipole polarizability of a black hole, things like that. But in the interest of not writing too many indices, I'm going to switch to a slightly different EFT, which has all the same properties, but I'm just going to imagine now asking the question of how a black hole responds to an external scalar field. I'm going to put a black hole in a background scalar field and see if there's any induced charge, things like that. Okay, but is this clear at this point? Yes.
We're doing this UV matching.
Yes.
Does it not matter that you would actually want to like have PNN coupled with gravity? Because you're setting boundary conditions sort of on the size, on scales of size R, right?
Yes.
And there you don't have to think about gravity and curvature.
Oh yeah. So here I was just doing like, I don't know, you have a chunk of metal in the lab and you want to like compute its polarizability. If it's a black hole, then of course you have the UV calculation is no longer Maxwell E&M. You have to do a calculation in like Maxwell E&M in say a Schwarzschild background. So there you do have to know about gravitational effects. Yeah, which I'll get to in a minute. But this was just sort of a warm up to show the interplay between this EFT and then the UV theory is like just some solving classical equations of motion kind of thing.
Does black hole does it have non-zero polarizability?
No, it does not at the end of the day. If I have enough time, I will explain. It turns out there's some symmetry that forbids it, which I will explain. So
Not some trivial symmetry like CPT or anything, but some not more non-trivial.
I think it's more not true. I don't know. I mean, maybe there's some like I'll explain. Maybe I would be delighted if there was some very simple way of understanding. I'll show you. There's like essentially what happens is there's a set of symmetries of the wave equation in a Schwarzschild Kerr background whose conserved charges sort of constrain these induced polarizabilities. I don't understand them in terms of like time reversal or anything like that. They're just some, yeah, it's still slightly mysterious to me. I don't know exactly where these things come from, but I'll show you explicitly what they are. Okay, good. All right, so what I'm going to do is, just for simplicity, okay, so I'm going to write down some world line EFT that couples the world line of a particle to a scalar field. The action here looks like the following. Now, instead of a Maxwell term involved, there's just a scalar field. And now on the world line, I'm going to include a bunch of couplings to the scalar field. Let me just write, this is the free point particle piece, which is not important, and I'm just going to write down the couplings of the point particle to the scalar field. So in principle, there's a monopole-like coupling, which for black holes is also zero because of the no-hair theorems. And then the types of couplings we care about are things which are quadratic in the field, because I'm always computing like linear response. And so I want to compute things which contribute to the equation of motion in a constant background for one of the fields. Okay. Possibly be things with more fields, more derivatives, stuff like this. This is just like the ELF multipolar response of the black hole to some ELF multipolar scalar field background. That's why it has L derivatives. This just means I'll subtract off the traces. And so roughly speaking, these things are what I'm going to define to be like scalar love numbers. Good. So now what we need to do is we need to compute the static response due to this type of coupling, both in the EFT and in the UV. So what I'm going to do is do the following type of calculation in the EFT. So this is the exact analog of the computation of electric polarizability I just did. So I'm going to turn on some background fields for the scalar, which looks like the following. So there's some normalization. Okay, so this is like a background field. You can think of it as something that goes like R to the L. And then I want to ask what field profile for phi gets induced. It'll go like 1 over R to the 2L plus 1. And if you actually just compute it, what you find is that phi of L is the following in the EFT. Oh, sorry, there should be some R's here, which are the dimensional scale, but I didn't put them. This is like the EFT calculation. Now we want to match it to a UV calculation and read off what these lambdas are. Okay, and maybe I should also have motivated why I'm going through all this pain. You might say, okay, why not just calculate these things in GR? Like, why are you going through all this trouble? It's precisely because there's been like a lot of debate in the literature about whether these love numbers are well defined, because in GR, you're kind of asking a question about turning on some source and asking how an object responds. And this sounds an awful lot like something which could be coordinate dependent. You're asking like how much something moves in a background gravitational field. So it's kind of sounds kind of slippery. But this is like completely unambiguous. I'm just like defining these responses as Wilson coefficients in an EFT. It's totally gauge invariant. There's no problem. So that's sort of the motivation for doing things this way. Okay, and so it turns out that if you do the UV calculation, all of these lambda L's vanish. Okay, so for a black hole, Lambda L is 0 for all L. Okay. Interestingly enough, this is something special to D equals 4. What happens in general dimension is if I define some L hat, which is L over D minus 3, then what happens is actually lambda L hat is 0 for all L hat, which you can see is all L's in D equals 4. Okay, now I'll explain this peculiarity at the end. Okay, so why do I care about this thing? So for me, this is like kind of a naturalness problem. I was there for the discussion at lunch. I don't want to wade into what naturalness means, but from the EFT, this is some parameter which is 0, which there isn't an obvious symmetry that sets it to 0. And so you might ask.
So, but for any D larger than 3.
Oh yeah, so in D equals 3, I actually haven't done the calculation, so I'm not sure.
For any D larger than 3 is.
Yes.
that number.
No, sorry. So in D equals 4, they're 0 for all possible L. In D bigger than 4, they're 0 if this L hat happens to be an integer. Oh, sorry. So L hat. Yeah. Sorry about that.
And for D equals 3, there's no black hole, right?
That's true, but you could imagine trying to compute this thing for like the BTZ black hole.
That's where the cosmological constant.
Yes, that's right. But I mean, you can do all of this stuff in ADS if you want.
But you're doing zero.
That's correct. That's correct. But that's just because, just for simplicity, writing things on the board. But all of the same techniques apply if you do things in ADS. So I think in principle that can be done, although I'm not aware of anyone actually doing the calculation in D equals 3.
And the results are also the same. The total lambda L are 0.
Yeah, it's an interesting question. There's an interpretational issue that maybe we can talk about, which is that, so you know very well in ADS CFD, like if you turn on a source, typically, I mean, yeah, if I just solve the wave equation in ADS and just demand regularity in the interior of ADS, then typically I get some admixture of the two fall-offs at infinity, right? And that, I mean, that's essentially what we would call a love number. So in some sense, even empty ADS has a polarizability in this sense. So it seems like that should be subtracted off, but I'm not sure how to do that systematically. So I don't know, there's some subtlety I don't quite know how to do with.
Also, I guess we have hair, so it can make things more complicated. But you can have linear terms, probably
In ADS?
like hairy black holes.
I don't know about these solutions. There are like things with stable hair in ADS.
I think so.
Okay. Yeah. I don't know. I haven't investigated the ADS case very systematically. All the all the UV stuff can of course be done in ADS. Maybe it's actually solving the equations that becomes kind of tricky, which I don't totally know how to do.
So these are non-rotating black holes, so these lambdas are 0 or?
Oh, it's actually true for Kerr black holes and also for Schwarzschild black holes. For a reason I will explain if I have time. Here I'm always talking about non-spinning black holes just for simplicity.
So my question was, in the Kerr case, in the Kerr case, whether this was 0, but there you can also interpolate, if you have an axion on some light scalar to a bow star.
Yes.
With some scalar hair.
That's right.
Would it also be vanishing in that?
No, so I expect if there's a like cloud around the black hole, that cloud typically will be formed. But the black hole itself, like a pure Kerr black hole, does not deform in this sense. Though there's a subtlety which I will explain at the end, which is that there is some tidal dissipation. So there is a response if you turn on a tidal gravitational field for a Kerr black hole, because the black hole is spinning, it will look like a time-dependent source. And so the black hole will like slosh a little bit, and there'll be some dissipation associated with this tidal background. And that looks like some response, but it'll be a pure imaginary response. It's a dissipative effect. So here, I mean, yeah, okay, this is like a subtlety that I'm happy to discuss more. So here I'm always talking about conservative responses, which correspond in this language to these Yeah, so these guys are always real because they're like coefficients in some EFT, and they capture the conservative response of an object. If you couple the world line EFT to like some other sector, you can capture the dissipative response of the object. And that's like, if you integrate out those additional degrees of freedom, you can get effectively complex couplings. And it turns out that these dissipative responses correspond to complex couplings computed in the UV theory, which I'll show you an example in a little bit. Okay. Okay, yeah, so I mean, the thing that got me interested in this, like I said, is that this seems something like a naturalness puzzle. And so we can get some insight into whether this is really a naturalness puzzle. Like, you can never really understand naturalness in the EFT. You always have to go to the UV theory. And so we can kind of understand what's going on by actually just examining the UV calculation a little bit more carefully. Okay. I don't know. Okay. I will try to speed up a little bit. Okay. So UV calculation is a calculation of black hole perturbation theory. And so what we want to do is, I mean, now I just asserted that these things were zero. Now I want to show you why they're zero by actually just doing the UV calculation. So let's start with Schwarzschild. And so what the UV calculation is I just want to put a scalar field in this background. And then I want to take the Klein-Gordon equation in this background, decompose it into spherical harmonics, things like that. And then I want to solve the Klein-Gordon equation subject to some boundary conditions. The Klein-Gordon equation in the static limit. So I'm computing some static response. So I'm going to set the frequency to 0 in the static limit. Klein-Gordon equation is very simple. This is also in L space. Okay. And so what I want to do is just solve this equation subject to some boundary conditions. But maybe first I should explain what the solutions kind of look like. So this thing is a hypergeometric type equation. It has a regular singular point. So in the static limit, it has only regular singular points. It's a hypergeometric equation. It has its singularities as r equals 0, rs, and infinity. The one at r equals 0 we don't really care about. We're always going to like match things between the horizon and infinity. And so you can just draw a picture of like what the solution should look like near r equals rs and r equals infinity. Okay. So near r equals infinity, there are two fall-offs. They're the same thing as in flat space. There's one where phi goes like r to the L. There's a fall-off where phi goes like 1 over r to the L plus 1. Near the horizon, there's also two fall-offs because it's a second order differential equation. There's one where phi goes like a constant, and then there's one which diverges at the horizon logarithmically. Good. And so roughly speaking, the boundary conditions that we're going to impose, we're going to demand that the solution for the field is regular at the black hole horizon. So we're going to demand that there's a single fall-off at the black hole horizon. And then the whole question of computing these love numbers, the love number is roughly speaking the ratio of this fall off to that fall off. And so I need to figure out how to extend the solution, which is regular at the horizon, out to r equals infinity. Okay.
So you don't care about the energy. You're allowing the thing to grow.
That's right, that's right. So I'm imagining there's some external sources that, I mean, the problem is really phrased from the outside in, but I'm phrasing it from the inside out. From the outside in, what goes on is I have some external sources. I don't know, I have like a big moon or something I move near the black hole, and it induces some phi goes like r to the L profile, which I'm imagining this moon is like some external source. And then the black hole will respond in response to that exterior probe. The physical assumption is that everything stays regular by doing this, because I'm not doing anything like particularly violent. And what will happen is the solution will deform, and typically some subleading tail will get induced. That's what happens in electric polarizability. The interesting thing for black holes is this doesn't get induced. They like don't respond. You put like a moon near them and they don't deform. That's sort of the interesting fact. Okay. All right, good. So yeah, we just want to figure out how to connect these two solutions. This is the mathematical statement of what this love number problem is. I have a solution to a differential equation expanded in one asymptotic regime. I want to expand it around a different regular singular point.
So it's completely linear in phi, there is no back reaction.
Yeah, everything here is like in linear regime. Okay.
And sorry, this works. Black hole perturbation theory.
Yeah, it's a fancy word for linearized fields in a black hole background. Sorry, this is just what it's called in the literature, but it's really just let's do linearized solve the wave equation and fancy words for something simple.
Wait, so gravity is totally non-dynamical.
Here I'm fixing the background. So yeah, all I'm doing is solving for the behavior of a scalar field in a totally fixed gravitational background. And the reason I can get away with this is what I'm trying to solve for is sort of the leading behaviors as R goes to infinity. If I wanted to systematically correct that, I would have to start keeping track of the fact that phi and the graviton talk to each other. But well, another way of saying it is I've resummed many of the effects of gravity into the gravitational background. But if I wanted to ask like a nonlinear question, I would have to start caring about dynamical gravity. So if I wanted to indeed like ask some question about back reaction, I would need to consider couplings between phi and the metric fluctuations around Schwarzschild.
Is the belief that if you did that, the love number would still be zero? Or?
I'm not sure that okay, there were some limited calculations where people have tried to compute like nonlinear tidal deformabilities, and I think they're still zero, but I don't understand the calculations extremely well. But I think you can always, I mean, this is a well-defined question to ask it in sort of linear response theory. I don't know whether there's some nonlinear response that would be encoded in even higher dimension operators here with like more phi's and couplings to gravity and stuff like that. So I don't quite know what those would look like. So this is sort of the simplest possible response you could ask about. Okay. Good. All right. So the boundary conditions that I'm going to impose. One is I'm going to demand regularity at the horizon. So this is sort of the important / interesting one. And then the other one is kind of boring. I'm just going to normalize the solution in some way. Okay, but all the physics is really in this one. This is the one that's selecting the non-trivial solution. Okay, so it turns out that subject to these boundary conditions, the solution to the wave equation is very simple. It's just a polynomial. Okay, and so what does that look like on this little plot? There's a solution which is constant at the horizon, and near infinity it just goes like r to the L. And this is like the mathematical way of explaining or stating this sort of surprising feature about these love numbers. It's saying there's some differential equation where I have a solution. If I expand it in two asymptotic regimes, it has a single fall off, which is a very non-generic thing. Okay, so that's sort of the mathematical surprise about the vanishing of these love numbers. Okay, but maybe let me contrast for you sort of physically what would be different. So imagine that this thing were not a black hole, it were instead a star. The natural thing to do would be to impose some boundary condition at some intermediate radius, which is like the surface of the star, which is much larger than our Schwarzschild. And I just impose some normalization of the solution at this radius. So there's no longer this demand of regularity. And what generically happens is if you expand that thing near infinity, you get some admixture of both of these two fall-offs. And so, you know, a random star will have a love number.
This is like very similar to, I think, Bekenstein's proof of no scaling. I think it was Bekenstein.
Yeah, it's, I mean, good. So Bekenstein's proof is indeed very similar, and it relies on basically the same phenomenon. It's kind of a genericity statement. So Bekenstein is sort of asking the following question, like, imagine you have a solution that has this fall off at infinity. What does it look like at the black hole? And so here's something very non-generic happened. I got a single fall off in both regimes. But if I ask that question, if I say, okay, what happens to the solution that has a single fall off at r equals infinity? It's an admixture of these two fall offs at the black hole horizon. And so it's singular, and then you would say, okay, there's no hair, right? Because that's what we mean by hair is having a bare 1 over r to the L plus 1 term with no corresponding source. Okay, so it's, yeah, so I would say Bekenstein's statement is a statement about the generic thing, your generic expectation actually happening. And the vanishing of love numbers is kind of like a surprising thing. It's like a statement that the non-generic thing happens.
Austin, can you build a star that looks like a black hole?
Um,
In that sense?
yeah, it's a very good question. I don't think so. I think
Like the radial profile is something would go wrong with the. You can't fine tune the radial profile of, I don't know, density or whatever to keep on canceling love numbers.
Maybe a fuzzball. I don't
yeah,
know
it's,
what the love
it's an
numbers are.
interesting question. I don't know. I mean, you could ask, there are like there are these like black hole mimickers. Like people have some ideas that there are ultra compact objects whose size are about our Schwarzschild. And in the very few cases where there actually is an available interior metric, it turns out that they have a love number which is basically proportional to, I don't know, roughly speaking, how close they are to being a black hole. So I kind of suspect the only way to get the love number to vanish is to like impose regularity at RS. And if you impose any boundary condition away from R equals RS, you'll generically get an admixture of fall-offs, whether you can like.
But if I build a star with a density profile that I completely choose free function,
Yes.
I can't. You're saying I won't be able to, you know, get any.
Honestly, I don't know. That's a good question. We should try. I don't know. Yeah.
How does this blow up at the horizon is not work artifact, and given the fact that these Schwarzschild coordinates are great at the horizon? How do I know that-
Yeah, good question. So, okay, so here, this is a scalar field. So it's obviously coordinate invariant if it blows up. You might have complained if this were like a spin 2 field, you say, okay, that, I mean, give me some curvature invariant, but you can indeed check that curvature invariants blow up if these metric solutions have this log behavior at their horizon. So something really is singular. You could say, okay, do I really care about that? I don't know. I mean, it's sort of a physics assumption that things should be regular at the horizon. Okay. All right, sorry, I apologize, I'm basically at time, but let me just explain this pretty quickly and then call it a day. Okay, so this, okay, so first of all, what we need to do is to match this solution to that solution. Notice this thing is a pure polynomial. So the only way to match this, so here, this is just the solution at leading order in R. So I'm just really capturing this R to the L behavior. There are some subtleties that you might be worried that there's some mixture between the two fall-offs, but you can always cleanly separate them. So this 1 over R to the 2L plus 1 just doesn't appear here. So to match to this solution, I set lambda L to 0. So by doing this UV calculation, I've computed the love number and I see it's 0. Okay, so that's fine, but why is it 0? That's sort of the interesting question. And it turns out there's a bunch of symmetries. They kind of organize themselves into some ladder-like structure. And so roughly speaking, we can understand it in the following way. I can write the static Klein-Gordon equation in a way reminiscent of a Hamiltonian. I'm going to define the Hamiltonian like this. And it turns out that I can write this Hamiltonian in terms of some raising-like operators. The Hamiltonian can be written in the following way. Okay, where these operators are defined in the following terms of PL plus minus this. And then it turns out that these operators have a simple algebra with the Hamiltonian. They just satisfy the following relation: HL plus 1 DL plus DL plus HL minus 1 DL minus L. Okay. And so, for example, if I have a solution phi L that's killed by HL, then this implies that DL plus phi L will be killed by HL plus L. Okay, so if you hand me a solution at some given level of L, I can just act with these D plus and D minus operators to generate solutions with L plus or minus 1. And so then we would just want to exploit one further fact, and then I would stop.
Is it like an SL2?
Sorry? Yeah, good. So, yeah.
Delta?
Sorry?
What is delta?
Oh, sorry. Delta is this thing which is R minus R. Okay, so then the point is I just want to take advantage of the fact that something very simple happens at L equals 0. Yeah, so the simple thing is just that at L equals 0, the equation of motion is just like delta dr delta phi 0. So this thing has an additional symmetry. This thing transforms by like delta dr. And so then it turns out that, okay, so from this you can figure out that R equals a constant is a solution, and then by raising that solution with these ladder operators, you generate these finite polynomials that I was talking about. But also you can raise and lower this transformation to get symmetries at each order in L. These things kind of arrange themselves into some ladder-like structure. So roughly speaking, there's some, you know, it's like L plus 1. At L equals 0, there's kind of an accident that there's some extra symmetry. Then you can use these operators to generate Q's at these various levels L, which look like the following. Okay, the Hamiltonian. And then you can ask, what are the conserved charges associated to these symmetries? It turns out what happens is that, sorry, I need the other black. Basically, the conserved charges let you match these two solutions while solving the differential equation. So here, let me get it right. This solution has like QL equals 0. But this solution has QL not equal to 0. This solution has QL equals 0. Solution has QL not equal to 0. And so if you demand that the solution at infinity has 0 charge, you can uniquely reconstruct the solution everywhere. If you know it doesn't have 0 charge, then you get some generically admixture of the two solutions. And then, okay, good. So you can sort of understand, there's some sort of geometric understanding of where these symmetries come from. You can translate that into the EFT that I showed you, and you can see that this symmetry forces all those EFT couplings that I wrote down to vanish. And so there's some symmetry that you can identify in the UV of the theory that when you go to the IR, you can see makes the vanishing of all these couplings natural in the EFT. So if you like supersymmetric quantum mechanics and stuff like that, it turns out that you can transform the Klein-Gordon equation in Schwarzschild into quantum mechanics in this Paschal-Teller potential. And then these raising and lowering operators that I'm writing down are just the standard like SUSY quantum mechanics raising and lowering operators that appear in that context. And then there's sort of one other interesting thing that happens for Kerr. So everything I told you was for Schwarzschild, but it turns out if you want to talk about spinning particles in a Kerr background. There's another set of raising and lowering operators where, okay, these fields are now described by the Tucholsky equation. So there's some equation governing psi, which now depends on L, and it can carry some additional spin label. It turns out that you can generate a solution at spin s+1 by acting now with some, or yeah, plus or minus 1, by acting with some raising and lowering operators now in spin on other solutions of the Tucholsky equation. And so, for example, you can prove that, okay, so it's easy to see that the equation for a scalar field in Kerr is very similar to a Schwarzschild counterpart. You can easily prove that the love numbers vanish in that context. And then you can use these spin raising and lowering operators to prove that love numbers vanish also for gravitational tidal perturbation. There's an interesting thing that in Kerr, the static response vanishes, but there is a dissipative response. It turns out that dissipative response is exactly these charges. They're non-zero for a Kerr black hole, but their values are exactly this dissipative response, which is still slightly mysterious to me. But it's kind of an interesting fact. You can also extend all of this stuff to finite frequency. And in that case, these charges capture the finite frequency response even in Schwarzschild, which is kind of an interesting thing. Let me finally say that what's going on in general dimension. So notice that this whole structure, it was very important that you could get down to L equals 0 because you're using some enhanced symmetry at L equals 0. In general dimension, what happens is that the relevant Klein-Gordon equation can be cast in the following form. In terms of this L hat variable. So it turns out that the L hats, which can be connected to L hat equals 0 by integer steps, are the ones that vanish, which are exactly these ones where L over d minus 3 is an integer. So that sort of also explains why these values are special in general dimension. Let me stop there, but I'm happy to discuss more. Thanks for your attention.
Wonderful. Thanks very much, Austin.
Yeah, sorry for going over time.
No, that we harassed you enough. You certainly deserve the extra time. Yes.
I just want to clarify, the spin discussion is adding angular momentum to the black hole, but not changing what you're bringing, what you're probing with.
Oh, sorry. No, these guys are changing the spin of the particle. So yeah, so there's a first step, which is you have to, so there's a similar algebraic structure for a scalar field in Kerr, which is like the spin 0 Tucholsky equation. So it's very easy to see that all the same stuff goes through for that. And then it's slightly more complicated for, like, say, a spin 2 field in Kerr. But then you can exploit the fact that there's like this other way of raising the spin in order to like bootstrap the spin 0 Tucholsky structure to spin 1, spin 2 Tucholsky equation.
Can you do, is there any difference between fermions, like spin 1/2? Or is it not been?
Yeah, we didn't do it. That doesn't mean it's impossible. I don't know very much about the fermionic Tucholsky equation, to be honest, but yeah, I don't know. Yeah.
So how can a black hole deflect light if all those responses are 0?
So what I'm talking about is a static response. So it's like if you put a black hole in a constant electric field, for example, it won't polarize. But like deflecting light is a finite frequency phenomenon. It's like you send in a photon of finite frequency and something scatters or gets absorbed. So those types of finite frequency responses are non-zero. Yeah.
I was a little confused about the fact that you're just computing equations for scalar field in the static fixed geometry, right?
Yeah, that's right.
Now, I thought that you wanted to see if you impose some sort of static scalar background, whether that has impact on the stretching the black hole in terms of changing the metric. I don't know.
No, good. Yeah. So there are various questions you can ask. The question I'm trying to ask is exactly the analog of like electric polarizability. So what's going on there is like you apply an electric field and you read off the response again in terms of that same electric field.
Yeah.
And so what's going on here is I'm applying a scalar field, and then I want to read off the fall off of that scalar field. And you can understand, I mean, I was just trying to give it some physical words that, you know, the black hole is doing something that's inducing this subleading scalar field fall off. Like if such a thing existed, it would be because the black hole, something, you know, deformed in response, or, you know, there was some rearrangement of something which led to this subleading fall off. But you can ask this question holding the black hole background fixed. Does that make sense?
Yeah.
But of course, you could ask the same question for the metric perturbations themselves. You can ask, if I turn on a tidal gravitational field, how does the linear metric respond? That also vanishes.
So should I think that Schwarzschild backgrounds have in full some hidden supersymmetry, or is it really just this one-dimensional problem?
No, that's a great question. I don't know. I mean, yeah, this is some symmetry identified in like a very, very special corner of linearized fields around Kerr or Schwarzschild. You might dream that there's some nonlinear version of it, or it applies in more general scenarios. I don't know. I mean, that would be very nice.
Wild spectrum. Is there any connection with the SL2R and sphere scribe or soft symmetries? Like
There's some connection to, so I guess Sergey is coming in a couple of weeks. He'll tell us about it probably, but there's some connection to the near horizon. There's a way of taking the near horizon limit where there's like an SL2R. So in Schwarzschild, you can see it geometrically, like the near horizon region is like an ADS2 cross S2. And so the part of, this SL2 that we're seeing is actually part of like the conformal killing symmetries of this geometry, but Sergey has a nice story about like the literal symmetries of that ADS2. But that's in that special case. In, yeah, for general curve, for like the metric itself, for like spin 2, I don't know exactly the geometric story. So, but I mean, I understand the geometric story in some limited setups, but I suspect there's like a better understanding of the geometry.
No further questions, and let's thank Austin again.